This is a presentation on how to apply the heat diffusion equation in your heat transfer analysis. Let us consider the first example. A slab of thickness L with constant thermal conductivity K, in which energy is being generated in the slab. It is no particular material, and therefore you do not have to look into the appendix for the thermophysical properties. Yes, you are asked to write a mathematical formulation of this heat conduction problem. It doesn't have to be solved. So let's have a look at what is meant by the mathematical formulation. The first thing you have to do is, of course, to sketch a schematic diagram of the problem. Don't worry if you are not Monet or Picasso, as long as you understand the sketch yourself, which value goes where. Then you have the assumptions, very important in heat transfer analysis. Steady state, constant thermal properties, isotropic material, one-dimensional in x, x being the horizontal direction here. Then you have the full heat diffusion equation in Cartesian coordinates, three-dimensional unsteady. But with the assumptions, you will end up with the simplified ordinary differential equation here. And you have two boundary conditions since it's a second order ODE. The first one being for the insulated surface, and the second being the one exposed to the surrounding fluid with the convective heat transfer coefficient. So this is enough for the mathematical formulation, the ODE and the two boundary conditions. If you want to proceed to try to solve this, see, you may integrate the ODE, integrating once, integrating twice, and you have two constants of integration, C1, C2. If you apply the first boundary condition, that is on the insulated wall at x equal to 0, okay, you will find that C1 is equal to 0. So you have a quadratic temperature profile within that slab. It's quadratic, not linear, because you have different boundary condition on both surfaces and heat being generated within the slab. You apply the second boundary condition, the convective heat transfer boundary condition, and then you see why I have let constant A to be equal to minus Q dot over K here, because then the thermal conductivity cancels out. And you have this solution which you can solve if you know any one of the, 3 out of the 4 parameters listed here: Q dot, H, T at surface L, and the surrounding temperature. That's it. Now, next we look at an example similar to the previous one, but this time with values given to the parameters. You have a 1 meter thickness iron slab. Heat is being generated at 8 times 10 to the power 4 watt per meter cube. The insulated surface is still insulated, but the surface 2 is exposed to heat convection of 400 watt per meter squared Kelvin. The surrounding is at 100 degrees C. You are asked to find the temperature at surface 1, the insulated surface, and surface 2, the one exposed to the surrounding. So again, you have your schematic diagram to understand which value goes where, and you have your list of assumptions. Very important. One-dimensional in X. Iron is pure. You will see later why I've stated here I'm using pure iron, not 99% or 80% iron. So here, the simplified ODE, we have to solve with the two boundary conditions: the insulated boundary condition, insulated wall boundary condition, and the boundary condition for the wall exposed to the fluid. Then you look at your appendix. You have to look at the appendix, and listed down you have two types of material: pure iron and 99.75% pure iron. So that's why I listed earlier my iron is pure. It's fine if you decide to take the 99.75% pure. But for the 100% pure iron, I'm taking the thermal conductivity at 400K to be 69.5. Now, if you have chosen AMCO, then your K would be 65.7 watt per meter per Kelvin. Now, someone may ask why at 400K? Well, I thought that is reasonable because the surrounding is at 100 degrees C, which is about 373 Kelvin. And heat is being generated within the wall. So you have here A, the value, but I'm not going to evaluate this quantity yet. Again, you shall see later why. So it's going to reduce accidental mistakes in your calculation. Then you have two boundary conditions. Applying the first one, the insulated wall boundary condition, C1 is found to be 0. Then you have your temperature profile within the iron slab. Again, remember that A is a constant with the heat generated value known and the thermal conductivity determined from the appendix. So, you want to know the temperature at the insulated wall as well as the one exposed to the fluid, but you do not know C2. So let's find C2. Remember that dt dx is AX. So applying the second boundary condition, yes, you find here that you will be able to find the temperature at the surface exposed to the fluid because you know all the other quantities. Here you see that why I've kept the A until the last minute where I can cancel the thermal conductivity. So I have only to substitute the value of the amount of heat generated. Please check the units as well. They should be match both the left and the right side of the equation. If you solve that, you'll find that the temperature on the second surface is 373 degrees C. How about temperature on the surface that has been insulated? Now you substitute that value into the temperature profile equation to determine C2, and once you find C2, substitute it back, put the surface to be 0, and you'll find that temperature on the insulated surface is 875.5 degrees C. It's high. That is that. Now, a similar example, but this time in spherical coordinates. So you see an iron ball of diameter 5 centimeter, everything else is the same. You're asked to determine the temperature at the surface. There is only one surface because it's an iron ball. Surrounding is at 100 degrees C. As before, a schematic of the problem should be sketched. So you have here, note that the radius is 2.5 centimeter because the diameter was given. Then you have your list of assumptions with an additional one-dimensional in R, different from the previous one-dimensional in X. One-dimensional in R because this is in spherical coordinates. You have the full three-dimensional unsteady heat diffusion equation in spherical coordinates. With the assumptions, you should get the ordinary differential equation as such. And simplifying again, I've made Q dot over K minus Q dot over K to be A for now. And then you integrate once, integrating it twice, you get the temperature profile within that spherical ball with two constants of integration, C1, C2. Now you have two boundary conditions. Here is a solid iron ball. The first one would be a symmetric boundary condition. So the derivative at the center is 0. It's almost like adiabatic. The second is the convective heat transfer boundary condition. So if you apply the first boundary condition, you'll find that C1 is equal to 0. So you have a quadratic temperature profile within the iron ball. Next, again, I've assumed that my iron ball is a pure iron. Again, you can also choose to have an AMCO. So the thermal conductivity will be different depending on the type of iron you have chosen. There is no other type, only these two types. So with that, substituting into my second boundary condition, and I'll have my temperature on the surface of the iron ball to be 101.7 degrees C. That seems reasonable because the surrounding is at 100. It's a heat being generated on the in the iron ball. The last example is a long solid iron cylinder of radius 5 cm. Heat being generated in the cylinder, the outer surface exposed to heat convection with the surrounding at 100 degrees C, and you are to determine the temperature at the surface. Okay, so infinitely long cylinder. Sketch of the cylinder. You have your assumptions, steady state, constant thermal properties, isotropic material, one-dimensional in R, pure iron ball. You have the full three-dimensional unsteady heat diffusion equation in cylindrical coordinates or polar coordinates, which upon the assumptions will give you the ordinary differential equation. And you have two boundary conditions. It's a solid iron cylinder, so you have the symmetric boundary condition at the center, as well as the convective heat transfer boundary condition. And you integrate, you will get the profile within the cylinder, which is dependent on the radius, because we have assumed that is one-dimensional in R. So if you use the first boundary condition, you'll find the C1 is equal to 0, the constant of integration, and your quadratic temperature profile within the iron cylinder to be as such. Okay, so that is for the examples for now.